Hello and welcome back to PC Retro Programmer. In today's video we're going to finish off our implementation of the midpoint circle algorithm. You remember in the previous video we've already drawn a complete quarter of the circle. We started with an octant from the rightmost point of the circle up and to the left, and we reflected that about the x-axis using a trick involving base relative addressing. So there's only two things that remain for us to finish our circle. The first is to reflect everything about the y-axis. So that'll give us the leftmost quarter of the circle. And then we need to reflect about the diagonals to give us the tops and the bottoms. So let's start with reflection about the y-axis. This turns out to be really straightforward to do. Basically, instead of starting at the rightmost point, which has x-coordinate x0 plus r, we're going to start at the leftmost point of the circle with x-coordinate x0 minus r, and instead of moving up and to the left, we'll just move up and to the right. But otherwise, exactly the same code can be used. And then of course we'll use the exact same trick for reflecting about the x-axis using our base relative addressing. And so that'll give us all of the points on the leftmost quarter of the circle. So let's take a look at the code that I've written for this. I've called this circle3.asm. Well, if you've been watching our videos on line drawing, you probably realize that not very much needs to change here. Basically, all of our decrements of x need to become increments of x. In other words, wherever we were decrementing the offset before, we need to increment it now. And wherever we were rotating our mask and color bytes to the left, we need to rotate them to the right instead. So this first portion of the code is exactly the same with one very small change. Basically, I'm going to need access to the arguments to the function when I come to draw the left half of the circle, and so I need to save the BP register because that's required in order to access the arguments, and we mess it up in our circle loop. So I'm going to save it by pushing it onto the stack here, and I'll pull it back off the stack later to restore it, and that way I'll get access to the arguments again. So the first portion of the code is identical for drawing the right arc of the circle. This is exactly the code we had in the previous video, pretty much. So I'm going to skip past that down to the code where we draw the left arc of the circle. So you see the first thing that I do is pop that BP register, so I've got access to the arguments of the function again. And now the code is exactly the same as it was before, but of course we need to start with x0 minus r instead of x0 plus r for the x coordinate. There is actually one very tiny change that I made here. Basically, previously I was actually adding x0 to the offset, and that doesn't actually work here. We need to really be subtracting r from the offset at some point, and so it makes more sense to have the lines in the other order, to put the x0 into the offset and then subtract r. And so I actually went back and changed the code in the first portion of the algorithm as well, but it's now an add instead of a sub. Just so that the code is exactly the same otherwise. So then there are only other changes for the main loop. As I said, we need to change all of our rotate lefts to rotate rights. So that's those here, and that's an easy change. And of course we had a sub with borrow here to subtract from our offset if the carry flag is set. Now we need to add to the offset if our carry flag is set, so it becomes an add with carry. Now you might worry that this STOSB is going to mess things up as well. After all, STOSB increments DI, which is where we have our offset, so surely we need to make that a decrement. But it turns out that this was already taken care of in the first portion of the code. Further down, we actually subtract 1 back off the offset to get it back to square. Instead of subtracting 8112 here, we were subtracting 8113. So that actually undoes that extra increment that the STOSB does. And so we don't need to change anything here because nothing's actually being moved when it shouldn't. So in other words, this code is now complete. Obviously, the code for reflecting about the x-axis is exactly the same as it was before. You can see that we just draw the 2 points, one with offset di and one with the offset di plus bx. This is our base relative addressing. And so that doesn't actually need to be changed. So everything's finished here, and basically we can now assemble this and run it to see what happens. Now, of course, we should expect to see 1/4 of a circle drawn on the right and 1/4 of a circle drawn on the left. So let's take a look and see if that is indeed the case. And yes, it is. Now, looking at this at the moment, it looks like it's drawn one side of the circle too close to the other, or something seems to be going wrong here. So I'll leave you to ponder that for the moment. Actually, this is a correct implementation so far. There's something else going wrong here, and it's an interesting thing to think about, and we'll discuss that a little bit later in the video. Now, just as we did for line drawing, in order to reflect about the diagonals, we just need to switch the roles of x and y in the algorithm. And of course, we're going to be starting at a different point. In fact, both of the pieces of code that we write for the top and bottom are actually going to start at the same point now. So it'll have x coordinate x naught and y coordinate y naught minus r. Remember, it's minus r because the coordinates go down as you move up the screen, and we want to start at the top of our circle. So basically we'll just start at the different point and switch x and y in our algorithm itself. This is actually not quite the algorithm that we implemented previously. Remember, we made a few small changes to this in order to make it a little bit easier to implement. But we actually don't really need to refer to the implementation. Once again, it's just a very simple change to the code itself to make it work in the other case. So let's have a look at the code that I've written for this. I've called this circle4.asm. Well, as you imagine, the first half of our code is going to be identical to what it was before. So we've got those two sections, and we've just added another two sections to deal with the tops and bottoms of the circle. Now, I've made one very tiny change to this first half of the code. Basically, instead of just popping BP so that I get access to the arguments again, I have to put that back onto the stack so that it can again be restored for the third and fourth portions of our code here. But otherwise, the first half of this code is identical to what it was before. So you can see in the third portion here, I pop BP, and again, I push it back onto the stack so we can restore it for the fourth portion of our code. But there's one additional very sneaky trick that I'm going to apply here. The starting points for the parts of the circle that we haven't drawn are the same. And that's a little bit different to before, where they were the rightmost and leftmost points of the circle. In this case, in both cases, we're starting at the topmost point of the circle. So we don't need to recompute the offset, color, and mask bytes for the fourth portion of our code. We can just reuse the values that we already computed in the third portion. And in order to do that, I'm just going to push them onto the stack. So the offset's in DI, and the mask and color bytes are in DX. So it's just two pushes. And then in the fourth portion of our code, we can just pop those back off the stack. Of course, everything has to come back off in the reverse order, so DX, then DI, and finally BP. And now we have access to the arguments of our function, but we don't need to recompute the offset, color, and mask bytes. In fact, this is the start of the routine here. So the lead-in here is very much truncated because of this saving that we've made. So basically, we need to look at the third portion of this code and see how it differs. It's pretty much the same as the first and second portions, but we're starting with different coordinates, and of course we're changing the roles of x and y. So our starting coordinate now is going to be, the y coordinate has to be y naught minus r instead of y naught. We're still having to compute the y and x parts of the offset just as we did before. It's just that the coordinates themselves have changed. So we get r and we subtract it from y naught, and then the code is identical for computing the y part of the offset. Then we have to compute the x part of the offset, and of course the x starting coordinate is x naught now. So we just move that directly into cx and add it to our offset, and then AND it with 3 to get x naught mod 4. And then from there on, everything is exactly the same for computing the color and mask bytes. And so the leading code is otherwise the same as what it was before. So then we come to the actual algorithm itself, and here is where some things start to change. Well, first of all, we need to set the initial value that we use for our base relative addressing. Remember, this is the offset difference between the starting point and its reflection about the x-axis. So previously we were starting at the rightmost point of the circle, and when you reflect that about the x-axis of the circle, you get the same point. So the offset difference there was 0. But here we're actually starting at the topmost point of the circle, and when you reflect that about the x-axis of the circle, you get the bottommost point. And so the difference in scan lines is actually twice the radius of the circle. So the offset difference now has to be 80 times r. It's 80 because there's 80 bytes per scan line, and it's just r because both of the scan lines are in the same bank of memory, so we're only counting even scan lines or odd scan lines. So it's just 80 times r, not 80 times 2 times r. And so we just compute that here. And that's the value that we put in bx to be used with our base relative addressing trick for reflecting about the x-axis. Further down you can see where we actually update that. You can see that we have to subtract 80 from bx. Obviously, as we're moving down the screen, that offset difference is going to get less, and again it's just going down by 80 because we're only counting even or odd scan lines. So the rest of the code should be fairly similar to what we've had previously. One thing we do have to worry about is the STOSB instruction increments DI, and we need to compensate for it, but we can't do that by making this an 8113 instead of 8112 in this subtraction. And the reason is because this is now inside the if statement, and so it doesn't execute all the time. This increment y has moved inside the if statement because we're switching the roles of x and y. And so we need to compensate that some other way. And the way it's done is exactly what we did in the line drawing. We set the direction flag, which decrements di instead of increments di here. And then that we can compensate for on the other side of the if statement here with our add with carry. And so that takes care of that problem. But other than just switching around the code for x and y in this implementation here, everything's pretty much the same as it was previously. So of course we have to clear the direction flag when we're done with that case, and it's always needs to be set to clear when you exit your function anyway, because that's what everyone assumes. So then there's the fourth part of our code, and there's really nothing to say here. It's exactly the same trick as we already applied earlier today. Basically, in order to draw the left-hand side of the circle, top and bottom, we just need to switch all our increments of x to decrements of x, and we already know how to do all of that, so I won't go through it in any detail. But basically that's the fourth case, and that's our full circle drawn. So let's save this code and then we'll run it and see hopefully our full circle. Now, as I was mentioning earlier, something is a little bit off with this circle, and you'll see that when I actually run the code, it doesn't look exactly round as you might expect. So let's see what's going on here. As you can see, it seems to be stretched vertically. Now, you might have already figured out why this is. It's because the pixels on the screen aren't square. And this is one of the reasons why I really wonder why the midpoint ellipse algorithm isn't described online. Since in order to draw a proper circle on the screen, unless you have perfectly square pixels, you need to change your circle code into ellipse code to compensate for the aspect ratio of the pixels. In fact, if I recall correctly, the aspect ratio of CGA pixels is 6:5, so we really need to draw an ellipse which has semi-radii in the ratio of 6:5, with the 6 being in the horizontal direction, so it looks more stretched in that direction, in order to get an actual circle on the screen as far as your eyes are concerned. So this is something that we're going to do in a later video to try and get an actual circle in CGA. It's a little bit of a disappointment having come so far, but there's nothing to worry about. There's really not very much of a change that we need to make in order to draw circles. Drawing actual ellipses of arbitrary dimensions is a very hard problem on CGA, and something we'll look at a little bit later. But it turns out that for circles with this 6:5 ratio, there's a trick that we can use that will enable us to do it quite straightforwardly.